So where does this fit in with what we've been talking about with Newton's laws and everything else to do with dynamics? Well, if we think about Newton's second law, and you don't need to know how to do this. It's not that hard though. But I want you to think about what this means for your egg experiment, because I think you've got to be thinking about the collision with the egg, and you've got to be thinking about that time for the collision. So we're not talking about the time it takes for the egg to actually fall from the top of D block or the top of wherever we end up having to do it to the ground. I'm talking about the collision time, how long the collision itself lasts, how long that force is applied to the egg. So it's not being applied all the way down, that collision force. It's being applied only during its contact with, like, between the two objects, between the ground and between the egg. So that's the force you're trying to like simulate in your experiment for the first part of your assessment task. So if you're sitting there going, I don't know that I've done that, go back and have a think about it. Send me a draft in, and I'll tell you whether, I'll give you some help to see how you're going, and like, ask me some questions about it, because that's what our draft policy is. Ask me, are you on the right track? Is this, and I'll see what I can do to give you a hand. Okay, so Newton's second law, the good old F equals ma. If we break that down, I want you to remember that acceleration is the same as velocity on time, so it's a change in velocity on time. So we can then therefore think of force as mass times velocity on time, and we know that mv, or mass times velocity, is momentum, so force is the same as momentum on time. So basically what we're saying, that if we transfer that around, if we rearrange that, momentum is just the force that's applied to the object times by the amount of time that force is applied. So I'll put it as a little triangle change in time here. Okay, so the amount of momentum that's transferred to an object due to a force in a collision is going to depend on the amount of time that force is acting on the object. And so that's how Newton's second law applies to this. And if we think about Newton's third law, we know forces occur in pairs. So if object A applies a force to object B, we'll call it FAB because it's A on B, then object B is going to apply an equal and opposite force on object A, and we'll call that FBA. So FAB equals negative FBA. You have to remember, though, that if you're talking about a collision between like a truck and like a Nissan Micra, whatever those tiny little cars are, they're going to apply the same force on each other, to each other, but their masses are really different, so the resultant acceleration is going to be really different. So don't go thinking, oh man, like, how does that work? It's like we're having that conversation about you applying the same force to Earth because of the attraction of the Earth due to your gravitational pull compared to the attraction of the Earth on you. So you're accelerating at a much greater rate towards the Earth than the Earth is accelerating towards you because you're tiny and insignificant. Okay, so just for this example, not in real life, everyone matters, everyone's important. Okay, so what does that mean for the first law? So we've done the second and third law. What about the first law? So if you think about the first law, it's the law of inertia. So things like to stay at rest unless you act on them, or they like to stay moving unless you act on them. So that's inertia. And momentum, like, whereas inertia applies to moving and still objects at rest, momentum only applies to objects when they're moving. So they have to be moving. But it's a similar concept because inertia, like if you've got an object at rest, more massive objects, it requires a greater force to move them. So you can see there's a link here, but they're not exactly the same. But you can see where I'm going with it anyway.